Okay, this is the second question for Impulse, and in my opinion, the worst question between both packets. This question actually is so bad. It's kind of hard to explain because there's like so many steps, which is why I'm gonna take my time explaining this. I've recorded this like maybe 8 times now, and every single time, like low key, I get lost in the sauce, and I think that y'all are gonna get lost in the sauce because there's just so much happening. So I'm gonna work backwards initially here, and I'm gonna go ahead and just kind of give the answer right. The maximum compression of the spring is just gonna be the change in x, and that is equal to mv over square root m plus big M times k or e. So why is that? What are we looking for? So there are two scenarios here, right? There is your before and there is your after. So before, the block is chilling, minding its own business, and an arrow is flying its way. And also the block is attached to a spring and nothing's going on here. It's just a normal spring. Then the spring gets pushed back because the arrow has now made contact with the block and its energy has transferred into the block. So the important thing here, right, to understand is that this is a conservation of energy question, which means, or sorry, conservation of momentum, which means the momentum in this before is the same as the momentum in the after. It's just simply the momentum is shifted from being in the arrow to hitting the block, and then in the after, it is now being fully pushed onto the spring and it becomes spring energy. So, how do we even begin to solve this with that prior knowledge, right? I'm going to set the momentums of the before and the after equal to each other. And I can do that because the momentum is the same before and after, right? So the before, right, going to be mv minus mv initial, which is equal to, and then this is going to be m plus big M. That doesn't look different enough. Time m big V. This is the momentum before, the momentum after. Why does it look like this after? Well, that's because once this arrow makes contact with the block, it's kind of a part of our quote unquote system now, right? So the mass of the arrow and the mass of the block have to be considered. So the mass of the arrow, which is big, small m, sorry, gets stuck with the block, which is big M. So the total mass, right, of our system after the collision is small m plus big M. They both will now share the same velocity because it's being transferred. Since this is technically one system now, they both have the same velocity going to the left, because it's being transferred. So this is going to be kind of like a coefficient, and this would technically multiply into those. But this is going to help us solve for V. On the before, the initial movement is going to be 0 from the perspective of the block. The block is not moving, but the arrow is moving. So since the block is not moving, we have to plug in 0 for velocity and just kind of cancel that whole thing out. So now we're left with this, and I'm going to solve for V. To do that, I'm just gonna divide this on over to that side. So now V, big V is equal to this over M plus big M. So this is what our velocity now is. So knowing what our big velocity is, the velocity once the two kind of combine, we can go ahead and begin to solve for x, right? So where is x in the spring present is present in the formula 1/2 kx squared. We're going to be using this. The reason for that, right, is this is going to be set equal to 1/2 mv squared. Why? Well, when the arrow is flying, it is purely kinetic energy. After the collision, all of that energy has gone through the arrow, through the block, and now it is being put onto the spring. So it's going to be spring energy is going to be equal to the kinetic energy that the arrow previously had. Again, it's a frictionless floor as well, which means none of that is being lost when the block is moving. So all of the energy here, all the momentum that this arrow is carrying goes into the block and then into the spring. So after the collision, the same energy, the kinetic energy the spring had, is now going to be spring elastic energy inside of this spring. which is why I'm setting these equal to each other. And now that I have something for the velocity to plug in, I can actually finally try and solve for x. So because of that, down a little bit. So because of that, I am going to remove the half on both sides, and I'm going to go ahead and change the mass here, right? It's going to be kx squared is equal to the mass will now be small m plus big M v squared. And that's because this is not me plugging in the velocity formula. This is just me changing the mass because after the collision, the mass has now changed. It's now the mass of the arrow and the block, which is why the mass is these two added together. If we knew the arrow was like 10 and the block was 5, this would simply just be 15, but we don't know that, so I'm going to just plug in the combined mass. Then we have to plug in the velocity as well, which we have solved for. That becomes, oops, that becomes kx squared is equal to m plus big M times, and then let me roll up a little bit, times mv over small m plus big M squared. And now we simplify. This part is what confused me though, like before I move on, right? I was confused why, like, why we're plugging it in twice almost. We're not plugging this in word for word. We're just changing the mass to be inclusive of both the mass of the block and the mass of the arrow, because now the collision has occurred and it being perfectly inelastic, you have to add the masses up. So this this is just the same m that's here. It's not being plugged in from here or anything. It's just that the masses have to be added up together. Anyways, this exponent can now be, what is it, like, distributed. So, whoa, where am I going, bro? So this becomes m plus big M times mv squared over small m plus big M squared, and then you're going to cancel these out. So you end up simply getting kx squared is equal to mv squared over uh, small m plus big M. Because again, right, if this is squared and we're canceling this out, it's only going to remove one of the versions of small m plus big M, so it'll leave the other one as well. And then we simply, uh, yeah, I'll divide first. Yes, we'll divide by k. And so this will also be divided by k. So it's going to go up here. So that's going to give us x squared, or actually, is that how I want to do it? Um, yeah, that is okay. The x squared is going to be equal to mv squared, and then it's going to be m plus big M times k, and then we're going to square root both of these. So then we get, sorry, our normal x is equal to mv over square root small m plus big M. Okay, those m's look exactly the same. Okay. The reason it's not squared at the top anymore is because the square root cancels out with that square on the top, so the square root only goes to the bottom. And that is our final answer. Oh my god. Like, this is so stupid. Like, this is the answer for that, and we have to do all that. I mean, I did write big to be fair. But essentially, how you solve this is by looking at it, right? Is you have to acknowledge that, okay, there are two time periods we have to consider. We have to consider before the block is hit by the arrow and after the block is hit by the arrow. Because it's a frictionless floor, none of the momentum is being transferred into the floor through friction, for example, right? All of the momentum from the before, the after is being saved. It's simply just changing location. It's changing from the kinetic energy in the arrow to the elastic energy in the spring. So by setting these two equal to each other, we are able to solve for the overall velocity, right? Because we don't know what the velocity is. It doesn't even like really mention that, except like it's has velocity v, right? We don't know what that means. So we can't really plug anything into this formula. However, by realizing that, okay, in the before, there's the kinetic energy from the arrow, and there's the lack of kinetic from the block, which is what cancels this out. This is going to be equal to the combined kinetic energy of both the arrow and the block, which is, or sorry, the combined momentum, I should say, right? So that means the combined masses are going to be times multiplied by the velocity, which is going to be the same between the two. So then we use this to solve for our velocity, which is equal to mv over small m plus big M. You hold on to this. Then we do what I said before and talk about how, okay, it goes from kinetic in the before to the spring to the after. So we set them equal to each other, cut out the halves, and we get spring is equal to kinetic with, that halves. Then we plug in the total mass, right? So we realize that, oh, wait, in the after, the mass of the situation is now the block plus the arrow. So we add it together, and then we plug in the velocity as well, which we solved for earlier, which gives us this, right? And it's velocity squared, by the way, which is why we distribute this. And then we just begin to solve for k. So we move k, we reduce this and cancel out one of the one of the squares, and then we move the k over, and then we square root the whole shebang, and we're left with x is equal to mv over square root m plus capital M times k. To be honest, if you don't get it, I don't get it either. I think this one's really stupid. If you can find an easier way to solve it, please let me know. This one's pretty dumb. But yeah, if you don't get it, I won't stress. I wouldn't stress because this is like not an easy question to get. So don't worry about it. But yeah.